Hi, in this lesson we'll take a look at scatter plots. You can see on the screen here we have some different scatter plots, some with positive correlations, some with negative correlations, and in the middle we have a scatter plot with no correlation. In this lesson you will practice drawing a scatter plot, also looking at drawing something called the line of best fit, and then also being able to look at graphs and describe relationships that are represented by scatter plots. A scatter plot is a type of graph that does show a relationship between two variables, between x and y. Sometimes the relationship is very scattered, and sometimes the relationship can be more positive or negative. What's important to note is that a scatter plot is different from the kinds of graphs we've been doing, because the graphs we've been doing are linear equations, which means they're very predictable. Scatter plots are less predictable. Our textbook talks about the three main patterns to look for, or the three kinds of relationships that we can have. The first one is a positive relationship. So this means as one variable increases, so does the other. In other words, when x increases, so does y. The second type of scatter plots we can see is negative relationship, where one variable increases and the other one decreases. So we can see this when x is going upwards, y is going downwards. And then the third type is where we have points that are scattered everywhere, and there doesn't seem to be a relationship at all. This is a no relationship scatter plot. First example is a positive relationship. If we look at this graph and we look at the labels, we can see on the x or horizontal axis, it's about the time spent studying in hours. And on the y or vertical axis, we can see the test marks in percentages. Now we know from our own life experience that sometimes you can spend less time studying but still get good grades. And so this scatter plot reflects that. Generally speaking, we can predict that if you spend more time studying, you will get higher grades. And we can see that we have somewhat of a positive correlation here because we can see that the dots are going upwards. So we do notice that this is a positive relationship, but it's not linear. It's not like somebody said, if you study 2 hours, you get 60%, 3 hours, you get 70%. 4 hours, you get 80%. We know that life doesn't work that way. But we can see the positivity in this graph. As a general rule, the more time you spend studying, the better you're going to do on tests. The second example is not in your book, but it's a graph that shows a negative relationship. It's a scatter plot, so again, it's not linear, but just because it's a negative relationship doesn't mean that that's a bad thing. Here we have on the x-axis the amount of kilometers run per week, and on the y-axis is a person's weight in kilograms. So a negative relationship here is that as you increase the time running, the chances are good that your weight will decrease. And so we can see a downwards trend with the scatter plot showing that type of relationship. But just like studying for exams, it doesn't necessarily hold true that if you run a certain number of kilometers, you're going to lose a certain amount of weight. Everybody's bodies are different, but we could make a general conclusion that the more you run, the chances are good your weight will go down. This scatter plot shows no relationship. If you take a look at the x-axis, it's all about the jersey numbers. This would be like a hockey jersey number or maybe soccer. And then on the y-axis is the goals scored. So even though we have a player like Connor McDavid who's number 97 and he does score a lot of goals, it's not based on the fact that his number is 97. It's his ability. And so here we can see that the plots are scattered all over the place, that there's no correlation between the number on your back and the number of goals you're going to score. When you have a scatter plot and you can see a definite relationship, you can draw a line of best fit. A line of best fit is a straight line that you draw through the middle of the points. So you try to touch on as many points as you can. And there's no perfect way to do this. The line of best fit is a way to show the average trend of the data. Is it going upwards? Is it going downwards? And a line of best fit is a way for us to predict unknown values because there is a pattern we can follow. We can only use a line of best fit when there is a clear relationship between your x and your y. If there is no relationship, like our scatter plot for our jersey number and gold, then we can't draw a line of best fit. There's no trend we can look at. Here's a graph about the population of Canada, and we can see on the x-axis it starts in 1950, and it goes beyond where we are today all the way up to 2030. We can see very clearly on the x-axis, or y-axis, pardon me, that we have the population in millions, and we're going up by increments of 5 million. So even though there are differences in the years in terms of how rising the population is going up, and it is a scatter plot because it's not perfectly linear, we can draw a line of best fit to show basically where's the middle of these plotted points and where are we going. So when we look at 2030 and we look across, is this graph reflective of where we will be at approximately 45 million people? So if you are trying to draw a line of best fit, you're going to try to hit basically at the average. So you're going to try to hit to show a line somewhere showing the trend, and that can be an upwards or positive trend, or it can be a downwards trend. So we're trying to hit the middle or the average when we draw the line of best fit. For the next portion of the video, we're going to take a look at two graphs in the practice exercises. We'll speak about scale and speak about setting up the x and the y axes, and then you're going to draw a scatter plot, and then you can also draw a line of best fit if you would like to. Question number 1 is not asking us to draw a line of best fit. We'll do the setup together. So here we're looking at a table representing winning times in a 100-meter race in 7 years. So I'm going to give this graph a title. I'm just going to keep it simple, winning times in a 100-meter race. And then I'm going to look to label and create my x and y axes. So my x-axis is the top one always, and my y is the bottom one. So I'm going to label x is going to be the year, and y is going to be the times, and the s there is for seconds. Now I'm going to figure out my scale. I've got 1950 up to 2005. Most of the time we're going plus 10, except for the last one. I'm going to start here at 1950, and I'm going to use a scale break because from 0 to 1950 I'm using 2 squares to represent a giant jump in time. From there I'm going to go up by 10 years, so I'm going to put 1960, 70, 80, 90, the year 2000, and then the year 2010. Note that 2005 is going to be in the middle between them. I don't have to label that. On my y-axis, I look at my lowest time, which is 10, and my highest time, which is 13. And I have to spread that out. And I see that I have a lot of decimals of 0.5. So again, I'm going to use a scale break, and I'm going to start at 10, and I'm going to use 2 squares to represent 0.5. So this is something that takes some practice, and you may have to erase sometimes to try to set things up. But your scale is very important. You need to have consistent scale, and that means consistent spacing for your numbers and how many grids you're going to use to represent those numbers. That's the hardest part of graphing, is setting up the X and Y axis. Now you can go ahead and plot the points based on the years, and you will have created a scatter plot. For B, the table represents the population in Canada in 7 years, so I'm going to give this a title, Population in Canada, and then I'm going to take a look at my X and my Y. X is the year, Y is the population in millions, and I take a look at my data. 1971 to 76 to 81 to 86 to 91 to 96 to 2001. That's a +5 pattern all the way through. So I need to space those out. Again, I'm going to use a scale break. I'm going to put 71, and similar to the last graph, I'm going to start to plot my years on the X2 grids for each +5 of the years. For the y-axis, I look at my lowest score, which is 21.6, and my highest, which is 30, and I can see the decimals are kind of all over the place. When this happens, it's no problem. You're doing a scatter plot. You don't have to have your plotted points exactly on the grid where they cross. So what I chose to do here is, again, a scale break, and I started at 21, and I used one box for 1. I couldn't fit in. This is where having a bit of your own graph paper might be better, because it's pretty darn tight in here. You may have a better way to set up your Y, but I couldn't find a good way to set up my Y where I could have it spaced perfectly. So scale is so very important. When you have the scale set up, then you can start to plot your points. So 1971, I'm at 21.6, so I'm just trying to kind of average it partway between 21 and 22. So I'm going to plot my point there. And 1976 can be right on the 23. And so we will see that this will show a line, but it won't be a perfect line. Population is increasing, but not exactly the same every 5 years. So that is why we have a scatter plot and not a linear graph for all of the questions in this exercise. So again, scale is very important. Even if your graph is a bit squished, that's okay. You don't have to make all of these decimals perfect and reflected perfectly on your graph. When you are doing a scatter plot, and even if you're doing a linear equation, you can have a point that is not on the perfect grid, such as this one here that I'm highlighting. That's okay. For the first few, you're going to do just the scatter plot, and then question number 2, you will create your graph, and then they do ask you to draw a line of best fit there. And if you find the graphs in your workbook a bit frustrating to work with, feel free to create your graphs on your own graph paper.